this time more coherent than the last, in every sense of the word. Right? Okay, so just mostly blah, 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 we already know. Part 2. Good stuff.
The
Okay.
revenge.
Say again?
The revenge?
Yeah, the revenge. Yeah.
Revenge.
Okay, so just a quick, okay, so first topic will be about this conjecture due to Kontsevich. So we'll say what it means, and it's not going to make any sense at first, and we'll try to unpack some of the definitions, so at least we know what parts of it mean. Okay, so just a quick recap of what we talked about last time was basically we saw this phenomenon where for any sort of Calabi-Yau threefold X, there are some exceptions you have to be careful about. There seemed to be another one, another CY3, which I'm writing as X check, with the property that there was this is what we call the mirror, where if you took the Hodge numbers of the first one, it would look something like this. So you get this nice little diamond, and it's entirely determined by these two integers, a and b, positive integers. Then this other one, this X check, should have the mirrored Hodge numbers where a and b get swapped. So it seemed empirically like, at least for a lot of Calabi-Yau threefolds, there is this mirror partner that first we just saw it as coming out of many examples, right? You looked at a lot of data points. And then this was supposed to be kind of the tip of the iceberg of a more general correspondence where we had all kinds of things about X related to very different looking things about X check. For instance, so here we had the these Hodge numbers. But there were other things too, like we briefly mentioned, without really giving any definitions, but just as part of the story, that there's this connection between counting curves on X, which is basically, if you get into the details of it, it's computing these things called Gromov-Witten invariants, and that was related to integrating holomorphic differential forms on X check, which there were a lot of techniques to do, so this is how people came up with those stunning enumerative results in the 90s, and many other things that I will just not write at the moment, but basically all this stuff was supposed to be related to the symplectic geometry of X, and this stuff was related to the complex or algebraic geometry of X check. So this is just something that I hinted at as a teaser before. We didn't really say much about what this correspondence is supposed to mean. It's pretty vague still. But that was the hope, that there is some kind of relationship. Like to every Calabi-Yau threefold, there's a different one where the symplectic and complex structures get interchanged somehow. Okay. So also I should mention, because I'm going to be making this, I'm going to be kind of sloppy with this. I'm going to use these pretty much interchangeably a lot of the time. So for those of you who have not seen a lot of algebraic geometry, there is a result that as long as you're talking about projective complex manifolds, complex manifolds that can be embedded into projective space, these are actually the same thing. This is a result of Sarah called Gaga. It's French for like geometry algebraique et geometry analytique. Analytic geometry and algebraic geometry. Turns out as long as you're in the projective setting, that basically everything you can say about homomorphic functions and this and that actually is true. You can just restrict your attention to algebraic stuff. We're not going to need details of that, but the point is, don't get freaked out if I just kind of am a little bit loose with whether I'm talking about complex, holomorphic stuff or algebraic stuff. So the goal of today basically is to make a little more sense of this in like a deeper way than just these numbers being the same. Okay, so there are a couple of ways that people have tried to summarize this or pack this into a big phenomenon. And I'm specifically going to talk about this one back from 1994 due to Kontsevich, which is called the homological, in the sense of homological algebra, mirror symmetry, or I'll just call it the homological mirror conjecture. So I'm going to write down something. It's not going to make any sense, and then we will try and define some of the terms as we go along. So what is this? It's basically that, so if you have, so for, again, you have to exclude rigid Calabi-Yalls, things like that, but we're not going to get into that. But for basically any Calabi-Yall, and now I'm not restricting to dimension 3 either, so that's kind of interesting. There's a mirror partner, mirror Calabi-Yall X check, same situation, but what do we want to say about them? Such that, okay, so we're going to phrase this as, word homological is a bit of a tip-off. It's going to be as an equivalence of two categories. They're supposed to somehow encode, there's going to be a category that's supposed to tell us something about the symplectic geometry and a category that's supposed to tell us about the complex geometry. So what are they? Again, just going to write them, and then we'll try and make sense of some of it. Okay. So this is the nice little one-line summary. The names of these things are, okay, this is the Fukaya category of X. You can associate such a thing to any symplectic manifold. Mohammed told us a bit about this a couple weeks ago. We are going to focus, as promised, mostly on this side. So this is the so-called category of coherent sheaves on X check. We will actually look at some definitions in that case, so that's good. It's not all going to be just inspirational fluff. And then the D's here, so we're not even saying that, okay, there's this category associated to the symplectic stuff, there's this category associated to the algebraic stuff. We're not saying that those are the same. There's one more step. This means the derived category, so we'll also touch on that briefly. And the B is a slightly technical thing, it's the bounded derived category, anyway. But those are the names. Okay, so no math yet, really, but naming things. Okay, so.
I have one question.
Yes.
Are the mirrors, do they have to have the same dimension?
Yes, yes. So yeah, the mirrors are of the same dimension, a good question. So, let's see. So what do we, just before we get into it, in keeping with the survey aspect of this, let me just mention what of this is known so far. So some cases have been proved. So the dimension 1 case, I mentioned last time that in dimension 1, Calabi-Yall manifolds are elliptic curves. That's all of them. So mirror symmetry, homological mirror symmetry, I'm just going to call it HMS from now on, was proved in that case fully by Polstrup and Zaslow, I think, in the 90s. Again, pretty early on, right? Because dimension 1, you might imagine, is the easiest case. So that is known. In dimension 2, so some special Calabi-Yalls are quartic surfaces in P3, so defined by a degree 4 equation. This is not all of them, but it's a pretty nice class of them. And this is known, but not all CY2s. And then, so the original inspiration came from dimension 3, from physics. And then there's a couple of other less catchy things, but for, I'll just say dimension n, we also know for abelian varieties, which is another way of saying certain So not every single, so when I say complex tori, I mean a quotient of Cn by a lattice. Some of them, depending on the lattice, can be embedded into projective space, and for various reasons, you may want to refer to those by this other name, abelian varieties, which are varieties that have a group structure and are projective. So this is a nice, also a different direction you could generalize the elliptic curve case to higher dimensions. So these are some of the ones that are known, but the original dimension 3, for instance, is still open.
Is that like a particular case or something like that?
Yeah, like a subset.
There, I mean, I think there must be, because like I'm not mentioning everything that's been proven, but these are some of the big, like easy to state families that are known.
But like
as you
there's
say,
no infinite family of Caravillas, three Caravillas that are known.
there may even, it depends on the infinite family, because like there are tons of families of Calabi-Yals. But I don't know much about the fine-grained, like what cases have been proven in dimension 3 and not. But at least like there's a lot left, that's for sure. Yeah. Okay, so that's kind of the status, and what I am going to want to say a little bit about towards the end today concerns, so this is all Calabi-Yau stuff. But even the simplest Calabi-Yau manifolds are not like super duper simple. Like elliptic curves are a nice playground for a lot of things, but you can go simpler. But you have to leave the Calabi-Yau setting. So there are generalizations of this to non-Calabi-Yaus. So I'm just going to mention that. In particular, there's another important family of algebraic varieties besides Calabi-Yaus, which we mentioned before are kind of, you can think of them as the flat ones. There's another important type of variety besides Calabi-Yau we can think of as flat. These are called Fano varieties. The literal definition that an algebraic geometer would give is you look at the canonical bundle, and if it's ample, I don't need that concept for the rest of this, so I'm not going to define it. That's what Fano means, but more geometrically, in the complex setting, this is actually, you can think of it as positive curvature. So for us, just to get like a lay of the land, there exists some Kähler metric with positive Ricci curvature. So, as opposed to flat, right? And then you have negative as general type. So for Fano varieties, there is another version of HMS, but the mirror is something a little more complicated. Rather than a Calabi-Yau having mirror another Calabi-Yau, mirror of a Fano is not another Fano or a Calabi-Yau. It's actually, in general, people, again, this is, the reason for this is some physics stuff that I don't know, but it works at least. So the mirror is something called a Landau-Ginzburg model, which is more intimidating sounding than it actually is. This is just, you look at some manifold Y, which generally will not be compact, and you look at a holomorphic function on it, which sometimes make it satisfy certain conditions, but more or less it's just you're encoding some geometric data in this function and its critical set, critical values and whatnot. So this is a non-compact, usually I guess we want it to be Kähler, but we'll see, actually I'll just mention now, the reason that I bring this up is not just for the sake of bringing up literally anything related to this that I can think of. It's because the one example that like there might be any hope of getting to in a setting like this is, so these are positive curvature, right? What's the simplest one? Well, in dimension 1, that's just P1, because this is topologically a sphere. So P1 is a Fano variety. It's kind of the simplest one you can come up with. And the corresponding mirror, in this sense, of course, you'd have to say what the categories are, because now I don't know what the Fukaya category of this is supposed to be anymore, because it's not the same kind of object. But putting that on hold for a moment, the mirror of this is, in this sense, it's a Landau-Ginzburg model. What is it? It's the punctured complex line and the function, let's say, z plus 1 over z. Very concrete. So we probably will not be able to get to that side of things today, but more or less you look at like the critical points of this and you draw some little arcs connecting them and like do some little topological whatever, and it's fun anyway. But yeah, we're gonna focus on the other side. Yeah.
Do you have to choose like which one do you take the Fukaya category of and which one do you take the coherent?
That's a great question. Actually, so the conjecture in general, it's supposed to work both ways, but you have to. There's a lot of different little variations on like what the category should be depending on the objects involved. So in this case, I'll just, again, there was a lot of me just saying things, which is a little unsatisfying, but at least there's something that's intriguing. You form the derived category of coherent sheaves on this side, and that's supposed to correspond to a variation of the Fukaya category called the Fukaya-sidal category. On this side, but you can also do it the other way around. If you think about the Fukaya category of this, that's supposed to be derived equivalent to something called the category of singularities here, which that's all I'm going to say. But there is a way to do it in both directions. There are various geometric physical reasons to try to guess at like what the A branes and B branes should be in both cases. Again, string theory stuff. Who knows? But yeah, that is one of the particularly neat things is that it does work both ways, right? Like given x, you get the x check, but also in reverse. Yeah. Okay. So basically what I think is realistic for today is to at least talk about what are coherent sheaves, what do they look like on P1, and what does the derived category construction mean, at least at a surface level. Okay, any other questions before we dive into that? Okay, great.
I have a question.
Yeah.
So is the isomorphism between the two categories in some sense, like functorial, in the sense that you have like a square of pairs, like x that goes x and x mirror and y mirror, and you have a map from x and y. First of all, is there a canonical map from x mirror to y mirror? If yes, is there a functor from like the derived categories? Does it gives like?
Not in any obvious way. So I think there is, it's the derived part of it messes that up a little. But there probably is some kind of like subtle data associated to a map, but I don't think it's as simple as just like if I have a map from P1 to something else, you don't directly get a map from the mirror of the other thing to this, whatever that would mean. At least I haven't, it seems like a very obvious
Also
question.
in the
But
case.
yeah.
Okay.
That seems like a pretty basic question that I've never really seen people talk about, which I'm sure someone has, but yeah, I think there's no like obvious functoriality in that sense.
Well, maybe the first question is the derived category a category? Or
Yes. So we'll get into like what kind of structure the derived category has. Okay, so okay, let me talk about coherent sheaves a bit.
because I know category is not a
Yeah. So there is actually this thing which there's a lot of, I have to be very impressionistic with some of the stuff. The Fukaya category is technically an A-infinity category, which is not a strict category in the usual sense. It's something close. Anyway, so coherent sheaves. Okay, so what are these things? Well, probably it doesn't require too much convincing that vector bundles are important in geometry. Right? They're very nice, very useful in all kinds of ways. fields and differential forms and all kinds of good geometric stuff, right? And topological things, but they have some problems, right? They have some, from an algebraic point of view, they're not so nice. Algebraically, and what do I mean by that? What is this vector bundle slander here? What I mean is, okay, let's look at a really simple example of a map between two vector bundles. So, to justify this horrible, horrible insult, let's look at E and E prime. Let those be trivial line bundles over R. Or C, it doesn't matter, but just this way I can really draw it literally. So here could be E, right? And this could be, for each point of R, I get a copy of R. Here could be E prime, exactly the same thing. And I want to make a map between them. So why don't I send a point ST, so this is referring to the base copy of R, and then this is in the fiber. I'll send that to ST. A very nice, well-behaved looking map to write down. It's algebraic, it's everything, right? It's nice and smooth, and it works, right? So this is a perfectly fine morphism of vector bundles, right? It takes each thing in the fiber here to the same fiber. What does it do? Well, on every fiber, except when S is not 0, it's an isomorphism. So you can think, right, like it sends, let's say this is S equals 0 here, and this is T equals 0. What does this do? So on, this fiber where S is 1 or something, it's the identity map. On this fiber, it just flips it upside down. So, but I shouldn't draw this on this one, I should draw it on the other one. It's kind of like this. At the origin, it sends 0t to 0, 0. In other words, it sends the entire fiber above S equals 0 to a single point. In other words, if we try to write down a kernel of this map, right, the kernel of the map on the S fiber it's nothing most of the time, and then it's the entire line in that one particular case. So the issue here is that if I tried to form a vector bundle that is the kernel of this map, right? I have a vector bundle here, a vector bundle here, I have a map between them. I'd like to talk about the kernel because I'm, coming at this from the algebra side, let's say. I can't make it into a vector bundle because, after all, around this, this S equals 0 point, it doesn't look locally constant, right? It doesn't look like just some product of an interval with either R or 0. The problem is that the dimension jumps here. So this doesn't, we can't assemble these into one big vector bundle that we would call the kernel of F. The problem is that the dimension jumps at the origin. Which is to say, in slightly fancier language, that the category of vector bundles is not an abelian category. We don't have all the kernels and co-kernels that we might want. That's all I mean by that. So when you think about like modules, for instance, or abelian groups, these are what we call abelian categories because any map in that category, you can talk about its kernel, its co-kernel, and you stay in there, which is a very nice property to have because that's kind of one of the main things we do any algebraic reasoning. So this is, from the algebraic point of view, this is not so nice. We have to leave vector bundle world to even talk about something so simple as a kernel. So coherent sheaves are basically the easiest or laziest answer to this problem. They're like, what if you took vector bundles and just added enough stuff to fix that? So the slogan that will carry forward, and I'll actually give some more precise stuff, but the slogan will be a coherent sheaf. You can think of it at first glance intuitively. It's like a vector bundle. except the dimension of the fibers can jump. So we saw that with this kernel where it was 0, 0, 0, 0. All of a sudden you had a copy of R and then 0 again. So it's not, you know, a nice like bunch of R's. There's that discontinuity of sorts. Dimension of fibers can jump. Okay, so that's going to be our slogan. So let's see, how do we actually formalize this a little bit? Okay. So I'm going to kind of cheat here, because to go the proper way from the beginning, like define a pre-sheaf, define a sheaf, define a ring space, sheaf of modules, would take too long and not be particularly interesting, right? This is something people spend weeks on, right, when you learn algebraic geometry. So I'm going to kind of give a hacky definition, which is still going to hopefully capture some of the main idea here. So we're going to look at, so for inspiration, I will, let's say, recall, which is always a funny word to use, because it's like, probably no one is recalling, but just to keep up appearances, we're going to say recall. There's this, for culture's sake, we should have heard of the Serre-Swan theorem, which there's a few versions of it. But the reason that I'm bringing it up here is it's going to give us a different way of thinking about vector bundles that easily generalizes. So what does this theorem say? It says, so in one case, and this is what Serre proved, if X is, let's say, an affine variety, so just something in, say, Cn cut out of polynomial equations, we can talk about, let's let R be the ring of regular functions on X. So all of the polynomial functions on this variety, the so-called coordinate ring. What does the theorem say? The theorem says that apparently vector bundles on X, so I'm using this to mean the category of vector bundles, algebraic vector bundles, so if you look at the transition maps, they're all algebraic. This is equivalent to the category of finitely generated projective modules over R. So certain modules over the ring of regular functions are, you can go back and forth between that data and vector bundles. This is just, you can also think respectively, this could have been a smooth manifold. Just maybe the intuition might be a little easier. This could be these smooth functions, the ring of smooth functions. And the same thing holds for smooth vector bundles. So we're saying that, you know, when you have a vector bundle, how do you get a module from it over the ring of smooth functions? You look at its sections. This could be something like, just to illustrate real quick, like if you have a smooth manifold, and maybe we look at the tangent bundle, right? So that would live on this side, and we're saying you can get a module out of that, a module over the ring of smooth functions. How? You look at all the vector fields, the sections of this bundle. This is a C infinity n module. In other words, you can take a vector field and you can multiply it by a smooth function. That's all it's saying. So we have a way of going from any vector bundle to a module over the ring of functions. Just look at the sections. And you can go in reverse, which is, in this, maybe in the smooth case, not quite as easy to describe. But the point is that you don't lose any data by doing this. But you only get certain special kinds of modules out of it. Right? You don't just get any module. And that's related to, you know, vector bundles are rather special. So you get rather special kinds of modules. Projective modules, I know some of you are doing algebra now, that's kind of a generalization of a free module. Free is a little too restrictive. Projective just means it's a sum end of a free module. But we don't need that. The point is it's a special kind of module. So what's the natural thing to try now if we want to generalize what these guys are? Just take off some of these restrictions. Okay, so that is going to give us our first pass at what a coherent sheaf is. So this is a sort of provisional definition. So I'll say a coherent sheaf on an affine variety to start with. So again, anything you can cut out with polynomial equations in Cn, I'll just keep it always Cn for today, is, I'm just going to define it as a finitely generated module over the ring of regular functions. So is, right, a finitely generated, I should say affine variety X, and I'm going to use the same notation, R is the ring of regular functions, so I just take away the projective requirement, which will turn out to be exactly what we need to get this kind of behavior. So it's kind of nice because for most purposes, when you're actually like dealing with these things, like if you're trying to do calculations, you're really just dealing with modules. Now this is a rather special case because I'm not talking about even P1, but that's kind of the start, right? What is a coherent sheaf? It's a finitely generated module. You probably maybe have heard the word quasi-coherent. That's just if you take away the only other restriction, any R module. So if you don't require it to be finitely generated, that's what's called a quasi-coherent sheaf. So aside from the fancy name, at least in this starting case, it is just a module. Okay, so of course we have to get to what about the not so basic case? What about P1? But let me pause there for a second. How are we doing? Okay. Okay. So now let me just give a quick example to see like how do we get this fibers jumping behavior out of this definition. In other words, what are the new modules that we just added in as possibilities here that will give us this jumping behavior? So this could be something like, so I'll just keep it really, that's like the simplest possible affine variety. It's the affine line, A1, or just C1 if you like. And in this case, what are all the regular functions on it? They are just the polynomials in one variable. You have schematic because, of course, C it has two real dimensions, but if we think of a line, what are the functions, algebraic functions on that line? They're polynomials. So apparently, according to this, again, kind of makeshift definition, a coherent sheaf on A1, on the line, should just be a CX module. So F on A1 is a finitely generated, CX module. And this is a particularly nice example because unlike almost every other example, we can explicitly describe all of these. So there's this famous structure theorem that we learn about in algebra, hopefully, that a finitely generated module over a principal ideal domain has a very simple description. So let's call this M. That it always breaks up into a direct sum of a bunch of, into a free part, a bunch of copies of the ring itself. So a bunch of CX's, and a torsion part where I, in this case, I mod out by some primary ideals. So power, well, in this case, they end up being powers of these prime ideals. So this is just purely the classification of finitely generated modules over a PID that gives us this result. So we have a bunch of copies of the ring itself, and then these quotients. So we could say this is the free part, and this is the torsion part, because each of these is a torsion module in the sense that, you know, you could multiply it by something and get 0, something non-zero and get 0. So what does this kind of mean geometrically? Like, trying to think of this in the generalized vector bundle point of view. Well, Cx itself, if that's supposed to be the sections of some vector bundle, it should just be the trivial line bundle. Those are the functions on the space. So each of these, now I'm going to use some notation that I technically haven't introduced because I'm doing this weird skipping over beginnings of sheaf theory thing. But let's just roll with it and see if it works. Each of these, so I'm referring to this as the functions on the space whose sections are Cx. So with this correspondence, this is how we would typically write the sheaf. And then what are these little torsion parts? So I'm just going to write it at first, say R1 times A1, and this is Rn times An. These are what you could call thickened skyscraper sheaves. So the terminology is suggestive, because if it's a skyscraper sheaf, well, that's exactly the kind of guy we were talking about before, where it's nothing, 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 and all of a sudden it jumps at one point. I'm being a little loose between like the fibers of the vector bundle and sheaves. You have to talk about stocks and things, but again, can't give like a full, it's not the point, right? I want to talk about mirror symmetry a little bit. So, and thickened meaning, okay, these give you some sort of multiplicity of that point. So if you have a positive power, you can think it's not just peaking at the point, it's a little bit fatter in some base sense. Again, not important for us right now, but, and this is just, well, it's certainly a sheaf of sections of a vector bundle, and not only that, it happens to be, in this case, a trivial vector bundle, just a bunch of copies of the ring of functions itself. So that's actually kind of nice. It tells us that we can, you know, in this case, so maybe this is like, you know, one of these little skyscraper guys, and this is just one of these. We can fully describe coherent sheaves on A1. They have a vector bundled free part, and they have what is new. In our generalization, we can also have these jumps from the skyscraper sheaves. And that comes from, on the module side, you can have torsion, which before we were dynamodeling. Okay, so that's A1. Really, our goal is P1. So I'll just say if I went up to AN, this becomes rather already a much more difficult classification problem, because classifying modules over a polynomial ring is a whole big issue, right? You can say some things. For instance, you know that the vector bundle part does have to be trivial. That's the famous Quillen-Suslin theorem, but anyway, should not be, I should not give in to the temptation to just mention every like passing interesting thing. So, okay, let's talk about what is a coherent sheaf in the non-affine case. Okay. Non-affine case now. Again, we're giving our like duct tape definition. So what do we want to do? Okay, so I'm going to use the idea of P1 as inspiration. So, for example, projective line. When we have varieties that are not affine, again, this is kind of a specific to algebraic geometry thing, because in the smooth setting, you don't really have such a distinction, but what is this guy? This is two copies of A1 glued together in some way. When I say glued together, okay, here's one little schematic we could use. You could say, okay, here's a copy of A1 drawn in a way that is going to be suggestive, and here's another copy of A1. And I want to identify them by taking the open, so these are glued along the open subsets A1 minus x the origin via this map, which is an isomorphism. So all we're saying is, okay, what is the projective line? Right? You look at an affine line, you take out the origin, you identify it with this other copy of the affine line by this relation x goes to 1 over x. So things close to 0 go to things close to infinity on the other line. So like if this is first copy of A1 and this is 0, for instance, that should be close to infinity, and the other one, you can see it's missing that point there. So from this description of a general variety we can think of as being covered by affine varieties glued in some way by isomorphisms, that gives us a notion of what a coherent sheaf should be in the non-affine case. Again, I'm eliding many things, unfortunately, about the foundations of sheaf theory, but the idea is a sheaf, if we're talking about them being something like sections of a vector bundle in certain scenarios, they should be some kind of locally defined object. In other words, I should be able to talk about sections over this open set or that open set. And in particular, perhaps that is, let's just assume that it's convincing enough for me to say now, coherent sheaf on P1 should be fully specifiable by a coherent sheaf on this particular part of it, as well as one on this part of it, and they have to somehow agree where they overlap. So a coherent sheaf on something that's not necessarily affine, I want to give a coherent sheaf on each affine. So let's say like a general coherent sheaf. There's a coherent sheaf on each open affine. Along with isomorphisms between the overlaps. Overlaps, okay. And they have to satisfy a cocycle condition, yada, yada, yada. But again, really I want to focus on the P1 case, so it'll be a little more concrete. So what are we talking about here? We're saying we have to give a coherent sheaf on the first A1 open subset. You can think, if you think of this as just like the line with infinity added, okay, we need a coherent sheaf on the non-infinite part, and then we need a coherent sheaf on the other part, which includes infinity but not the origin. A coherent sheaf on one of these or one of these is, as we just said, a finitely generated module over the polynomial ring Cx. So we need 2 of those. So what is the data of a coherent sheaf on P1? Very concretely, you can characterize it as you need a module here, you need a module there, and so where M is a Cx module, finitely generated. The other one should also be a module over the ring of regular functions on the other copy of A1, which it'll be slightly easier for me to write as, again, keeping this coordinate choice where I'm just describing one of these is like the finite part of the cover and the other one the one including the point at infinity. The other module should be a finitely generated C of X inverse module. And there should be some isomorphism on the overlap. So on the overlap where you're taking out 0 and infinity, what are the sections of M over that overlap? Well, there you're also allowed to multiply by X inverse because you took out 0. And then on M prime, you're also allowed to multiply by, well, you can invert X inverse. You can multiply by X now because you took out infinity. So again, this is maybe a little brutally fast if you haven't seen this before, but we're inverting X or x inverse respectively. So this is supposed to be on the overlap between these two affine pieces. We should have an isomorphism between the modules that allows us to identify one of these with the other. Okay, so basically, again, to give a slogan, a coherent sheaf is something like not just a single module in general, but like a system of compatible modules where you know how to go from one to the other. So people like to use the term in geometry, it's like a global version of the idea of a module. Not just one module, but various modules patched together somehow. And in the case of P1, it's just two of them because we can cover P1 with these two simple pieces, these affine pieces. So instead of just a single module, we have two modules and a way of connecting them. Okay, so that is the low-tech way of describing coherent sheaves on the projective line. Just like we were able to fully classify them for the affine line, you can do a similar thing here. Once again, I will just throw out statements as if they are God-given. This is not, the nice thing is this next thing I'm going to say is not too hard to prove, using relatively similar techniques to what we did in the affine case. The new interesting thing here is that, and this is what would show up now if you were to do this whole business with characterizing the derived category, but basically let me just summarize. So the coherent sheaves on P1, it's a similar kind of situation where we're going to have one part that is the vector bundle part, and another part that is this torsion part where you have the skyscraper sheaves, except now this can be a little more interesting. So I'm going to write it in a similar way as before. Okay, so previously we had a direct sum of, let me just call this a J or something. We had a direct sum of these skyscraper sheaves, or possibly thickened at certain points, and that is still the case. So on P1, on the projective line, right, there's infinity over here, you can have, in a general coherent sheaf, you can have something like this, right, where you have these fibers. Again, I'm just blatantly abusing this equivalence between certain aspects of bundles and sheaves, but you can have these points where all the action happens. And then you have this other part, so this is the torsion part once again. You have this other part where now it's a little bit more interesting than it was in the affine case. I've introduced this notation now. These are so-called, so this is the, let's say, locally free, in other words, vector bundle part, where these guys, this OK, what is that? That is supposed to be some kind of coherent sheaf that deserves a special name. These are the twisting sheaves. And according to my janky definition, we should be able to describe these in these algebraic terms. So each of these is kind of, well, almost as simple as we could make it. We take M to just be Cx. We take M prime to just be Cx inverse. So like the simplest module over this you could think of, except for 0. The simplest module over this you could think of. And the isomorphism of C, so twisting sheaves where theta, that is where all the action happens. It's supposed to go between Cx, except you invert x, so that's this, to the same thing. It's supposed to be an isomorphism of these as Cx x inverse modules. What could that be? Well, it turns out the only possibilities are, let's say S gets multiplied by some power of x. So this is a bit of polynomial algebra you have to fuss around with to show this for sure, but it's nothing deep. When you check the conditions, you find that these are the only possible ways of doing this isomorphism. And we just call, now I'm messing up my notation, I was calling this K. So the local aspect of it is the same for all of these. We have one copy of Cx, one copy of Cx inverse. How we put them together is a little bit different for each one. If that's perhaps a slightly less intuitive way of thinking about it, maybe the most down-to-earth way is the sections of these are basically just homogeneous polynomials of this degree. But anyway, the point is, coherent sheaves on P1, they have a similarly nice decomposition. The vector bundle part is a little more interesting because now we don't just have necessarily a trivial bundle, we have these twists, and then we still have these skyscraper sheaves that make it more than just a vector bundle. When did we start anyway? Was it 5 minutes late, 10 minutes late? Yeah, okay, so I'll just say something real quick about derived categories and that'll be it. Okay. So so far, this is the third portion of derived categories. Right, okay, so we did this, so now we have this notion of, can talk about all the coherent sheaves on an algebraic variety X, and that's supposed to give us some kind of data about the geometry in the same way that vector bundles would. And it's a pretty good invariant because in a lot of cases it determines X itself up to isomorphism. So for instance, if X is a smooth projective variety, there's the theorem of Gabriel and Rosenberg that this is the case. So this is a nice, it captures a lot, it captures everything apparently, at least in the smooth case. But it's not really what we need for the mirror symmetry setting, because you come up with this category on the other side, the Fukaya category, and there might be some intriguing connection, but they're just not the same structure. They're not equivalent. So it turns out, though, that they do share something in common. They are derived equivalents, and I'll have to say what that is. That's why we had the D's there. But not, it's too fine an invariant for the mirror symmetry purpose. C is too much for HMS. Okay, so what is a derived category, real quick? What is this, like, fuzzier relation that we need? So I'm going to momentarily change gears. And so there's a slogan when it comes to derived categories that I am shamelessly cribbing from, I think his name was R.P. Thomas. He said, he has a nice little article, Derived Categories for the Working Mathematician. The slogan is complexes good, cohomology bad, which to say cohomology bad, it's blasphemy, so I have to really spend a couple minutes justifying why I'm allowed to say that. It's like the worst thing you could say, right? Or homology, right? So what do I mean by this, and why would cohomology be bad? So I will, again, I'm gonna throw out a little recall here. Don't hold it against me. For those of you who have taken topology already, you would have seen the Whitehead theorem in topology, or a variant of it, which is that if you have two sufficiently nice spaces, X and Y, say CW complexes, and you have this continuous map, these are CW complexes, then actually you do get a lot out of, say, the homology groups. If this F induces isomorphisms on all of the, and let's just say they're simply connected to make this work, we need to assume a little more. If all of these induced maps are isomorphisms, isos for all n, then the map itself is something like that. It's a homotopy equivalence. But, so here's the tricky thing about this theorem, which is very nice because it seems like you can get all this data just from knowing the homology groups. You need the map, right? Like, you can't just say, oh, all the homology groups are isomorphic, therefore these are homotopy equivalent. You specifically need them to come from one map. And this is basically, I mean, there's other ways this comes about, but like this is, you could think, the nugget from which the idea of a derived category comes from. It's not enough, when we pass to the homology, we lose some information. Right? Of course we do, there's always this game in math of like, you want to throw away a bunch of information that you don't want, and then sometimes you do a little too much, and you go back and forth, you know, finer invariance, cruder invariance. But here, what could we do to salvage this issue of, okay, if we just look at hn of x, hn of y, it's not enough to recognize that it came from some map or not. So the idea is we want to, where do these come from? These come from the chain groups, or chain complexes, Cx, Cy. Instead of passing to homology, keep those. But now that's too much going on, right? Like you went too far in the other direction. What does this say? This says as long as you have a map from one to the other that induces an isomorphism on the homology groups, you want to consider these as being the same. So the thing is, if we have what we call a chain map from this to this, such that, so a chain map of this sort, which induces isomorphisms on homology, or cohomology, it all works basically the same way. So if you have the map already, we're building this into the definition, then, okay, we call this a quasi-isomorphism. This is just a homological algebraic term. We want to work in a setting where the quasi-isomorphisms make these equivalent, right? In other words, we want to work in a setting, in a category, where the quasi-isomorphisms are isomorphisms. But they're not, in general. So like you could, it's not hard to cook up an example where you have a quasi-isomorphism between chain complexes that are not isomorphic. So what do we do when we want to force the issue like this? We take some kind of, we need to impose some kind of equivalence relation, right? Or in this case, we want to formally invert every quasi-isomorphism. We want to just, by fiat, say, okay, the issue is I would like to consider Cx and Cy, when there is such a quasi-isomorphism, I want to consider them as the same object for this kind of purpose. And I can't, so because in general there is no inverse. So I just make an inverse up. So this is our favorite thing to do in pure math, right? Is just make it up and see what happens. So the derived category is actually, when you get down to that, I mean, working with it is another matter, but the definition is not too bad. The objects are just complexes. So typically, you would, in mirror symmetry, you would deal with the cochain complexes, but so complexes just, you know, you have a bunch of objects and they're, you know, d squared is 0, and okay. So the objects are, so derived category of, let's say C is some category where this makes sense, so it has to be an abelian category. The objects are simply complexes instead of individual guys. The morphisms, okay, get this is great. The morphisms are maps of complexes, except, so chain maps, right, the usual, if you have one complex and another, everything should commute, except now we also throw in, so one of these guys, so you have a chain map with formal inverses. You have to be slightly careful with all the set theoretic stuff to make sure that this works the way you want, construction-wise. Formal inverses for all quasi-isomorphisms. again, the idea is we want to consider things, quasi-isomorphic chain complexes as being equivalent, and this is the way we can force the issue. This is often described as it's a localization. You can talk about localization of categories. It satisfies the relevant universal property. And this is just kind of one way you construct it. So the morphisms in here look like if I have, x, y, z, if these are all complexes, and then maybe I have a map from y to z, and I have a map from y to x, and this is a quasi-isomorphism. Then in the derived category, I have a morphism from x to z because I have just made up, right? I inserted this formal symbol S inverse that now I can compose things with. So in the original category, there I just can't necessarily go back here, but now I can. And let me just wrap up real quick since that's basically out of time. What is the upshot of all this with like the symmetry stuff? So that's a definition of sorts. Again, like sweeping some things under the rug, but essentially, I'll just leave this as a teaser. There are some ways to get your hands on this kind of thing. Basically, you look for some kind of generating set. You look for certain special complexes that you can build the entire category out of. They have names for this, exceptional collection, things like that. And what it turns out is that, so just, I guess, it's not really a punchline. That's way too generous to say, but it turns out that also the B, I didn't say what the B is. The B just means you don't look at just any complex, you look at those of finite length. It's not important for this. It turns out that you can actually generate this entire derived category of coherent sheaves on Pn by certain special ones. It doesn't take that many. You just take a certain number of these twisting sheaves. I'm not saying exactly what it means to generate, but you take direct sums, you take kernels and co-kernels of maps, things like that. So you can build the whole thing out of a few of them. And in particular, for P1, it's just O and O1. And what you can do after a lot of chasing things around is it turns out that this is the same as you would get from, well, of course it is because that's what I said, but I didn't explain why in any way. But when you do this game with the topology of the critical sets of this thing, it's still not clear how to connect the two. The really lucky thing is, and this will have to wait for never, but this is the last thing I'll write, and then you all can go home. I know it's Friday, and everyone's probably tired of this. There's a bridge between these two. There's a very nice, another surprising connection here, that by looking at this kind of generating set, you can show this is actually equivalent. These are both equivalent to a third category. And what is that? I'm just going to drop this mic drop. It's the category, or derived category, of representations of this quiver. Boom. Anyway, and that's how you show that these. Okay, any questions?
Not that I can articulate.
That's my favorite. That's every day of my life. Yeah.
Yeah, I think I do have a question, but that definitely stopped me because I've seen that. So I'm thinking now.
Yeah, it's neat. This actually, it doesn't work for any curves except for P1, like higher genus curves. You can't find a quiver that does this. But it does work for other things in higher dimensions. You can, if you get lucky, you might find like a bridge like this. But anyway, it's not that exciting if you don't know anything about what this is supposed to mean. But it's neat. There's many things that don't look similar that apparently.
Yeah. So my question is a so general question.
That's all I'm looking for anyway.
Savage. But like, how on earth do we know that should be the right thing? Like what? Like
This thing or which part of it?
Like, for example, now that you show me what the the generating set of the coherent, the derived category of the lack of coherent sheaves in V1 is, how do I think that the other side is the correct thing to do?
Like this guy?
Yeah, like.
So there are various ways of trying to construct mirrors that I didn't mention at all, and I also don't know as much about that, but besides HMS, there's another point of view called the SYZ conjecture, which is more topological in nature. It's like Strumminger, Zaslow, and Zaslow, where it gives you, at least in some cases, a way of guessing at what the mirror should be. At least that's more, I don't know how that carries over to this non-Calabi-Yau case. The picture I've seen, again, this is, I'm going to say, because this, the picture I've seen is something like, if you want to look at like the mirror of a sphere, for instance, you're supposed to fiber it by tori, in this case circles. So you split it up as a bunch of circles, and then each of those, you look at the dual torus. In other words, in this case, you're basically inverting the radius. So like you get a circle of the same radius, and then this one is going to be a bit larger, and this one's going to be a bit larger. And so you get something like this, which is topologically a cylinder, but then you have to deal with the non-compactness somehow, and you have to put points on the end. But there is a way to kind of more geometrically guess at what the mirror should be, involving Lagrangian torus vibrations. There are other techniques, especially most of the examples that people do come from toric geometry, where it's more combinatorial, and so that's how people come up with mirrors. Now this kind of thing, there are reasons I don't really know how they come up with that yet.
This comes from physics.
Yeah.
So the theta is local lambda Ginsburg that comes from supersymmetric string theory, and the W map that refers to superpotential and supersymmetry.
Yes, that's the word. I should have used that word so you guys were like, oh, super potential. That sounds crazy.
Wow.
I don't know. I'm just glad it turns out very nice and simple, right? No decimal functions or anything like this.
Yeah, it's super.
I have a simple, more general question. Not
Yeah.
on this. So when you talk about the coherent sheaves,
Yeah.
over affine schemes, you can move to finitely generated modules.
Yeah, sure.
It's also more general, it works also over affine schemes.
Yes. So I was talking about everything over C, but yeah, the same notion works over an arbitrary ring. Yeah. So for an affine scheme, a coherent sheaf is literally a finitely generated module over that ring.
Can you do the same construction over the projective schemes and say the same thing when you
Yes.
define it over the open?
Yeah.
Okay.
Now, yeah, it works pretty much the same way.
So for elliptic curves, what can you say something about the mirror of an elliptic curve?
Yeah, so it's another elliptic curve, right? It has to be. And so the way that Polstruck and Zaslow proved HMS for elliptic curves, this is not saying much because it's elliptic curves. You have to do a bunch of work with theta functions, and then they have certain special properties where it turns out I haven't read through this proof myself. I just have heard of it.
Yeah.
But you look at different. So the curve is right. You can look at it as the quotient of the square, and then the symplectic side, you end up drawing special curves in here, checking the slopes and things, and I don't know. But there's an impressionistic 0.1% of. So I don't know what is involved in. I suppose the mirror of an elliptic curve, as far as which other elliptic curve, probably has something to do with some kind of involution of the lattice or something, but I don't know.
Okay.
Yeah, it's a good question.
Wait, I have a follow-up question.
Yeah.
From that. Are there elliptic curves that are their same mirror?
I don't know. I would guess yes. But, actually, what am I saying? The mirror is not necessarily unique because you can have non-isomorphic varieties that have the same derived category of coherent sheaves in some situations. So I don't know. I'd have to think about that.
So the conjecture is existence.
The conjecture is existence, and like you can't have like being derived equivalent does tell you something about the two varieties. Like it can't just be anything, but they're not necessarily isomorphic. You can have some sort of like an abelian variety and its dual, I think, are derived equivalent.
Do the proof of these things always try to construct a mirror, or
I
are
think
there a way to?
I don't know of any way of doing it without having a mirror in mind. I haven't seen that.
It's just, there's no way to show, that we know that is the only possible.
Yeah, and I also think that, you know, that you come up with some like candidate mirror in some way, often using ideas from physics, and then it seems to me like each case, I don't know, might be pretty different. Like here with P1, you kind of get lucky. One way to show that this works is to realize that there's this third thing that they're both equivalent to, and that doesn't always happen. And like elliptic curves, you have to really get like deep into specific things about elliptic curves, like to prove that case. And I don't know that I think the guy who proved it for abelian varieties maybe did some generalizations of that, but I don't think there's not much of a general framework. That's the thing. Like people are trying to grab this case and that case, and
There's lots of work.
yeah, that sounds like
Yeah.
Nice. Thank you.